Hey everyone, welcome into the second video on trig substitutions. In the last video we computed an integral where we made a trig substitution and it worked out. We got the right answer. It was an integral that we already knew the answer to. In this video I'd like to just kind of make a table or a chart or some kind of general method for making trig substitutions in integrals. So the basic idea here is that we want to integrate a function. So find the antiderivative of a function. And the function is going to contain a certain kind of, it's going to have a certain form in the integrand. And we're going to make a trig substitution to help us compute that integral. So like I said, I'm going to make a table here that we can refer to later. And the table is going to have 3 columns. It's going to say the integrand, that's the function f. Now, the integrand is not going to be exactly what we put in this table, but it's going to contain, it's going to have a certain form. We'll see. So then the next column will be the substitution that we want to make, and then finally the reason that we make that substitution. And so there are 3 different versions of the possible form of the integrand that we're going to want to take a look at in this video. And the first one is going to be the following. So our integrand could contain a term that looks like a squared minus x squared. So in this scenario, the a is always going to be a number. Okay, it's always going to be a number. And then the substitution that we should make at this point is going to be, and so up here I'm going to draw a unit circle so that we can refer to it as needed. But the idea here, the domain of this function, so the square root of a squared minus x squared, the possible values of x are that x can vary from negative a to positive a. That's it, right? If this becomes negative, then we don't have real numbers anymore, and we're only dealing with real numbers in this class. So the substitution that we're going to make has got to, it's got to cover all the values, either in the vertical or the horizontal direction here, from -1 to 1. Okay, so let me just write down what the substitution is. The substitution that we'll make for this one is that x should equal a, the constant, times sine of theta. And we want to make sure, so the reason I have the unit circle here is that we want to make sure that the domain of theta, so the allowed theta values, take care of all the possible values of x that our integrand is going to take on. All right, and so to do that, we need to make sure that if we're doing sine, we have to cover all the y values of our unit circle, right? So remember, this is the y-axis, x-axis, right? And so in this case, you could consider this circle to be x squared plus y squared equals a squared if you want. And then at this point, we need to get all of the y values, right? So we're going to take all the angles. So the domain of this function is going to be the right-hand side of our unit circle. And as we know, that means that our theta is going to be allowed to vary from negative pi over 2 to pi over 2. And it's allowed to attain either endpoint, right? So sine doesn't have any problem there. Now, whenever we make a substitution, an x substitution, we need to also compute the dx, right? And so dx in this case is going to be a times cosine of theta d theta, just the derivative of sine. And so this is the substitution that we'll make. Now, the reason that we make this substitution, we've partially thought it through, right? Part of it is based on the domain of the x that we want to make sure, the domain of the integrand, so the possible values of x that we want to make sure that we replicate over here with the integrand itself. But part of it is because with trig functions, we have Pythagorean identities, right? And one of the Pythagorean identities says that the square root, I'll just write this out, but hopefully you remember this, the square root of a squared minus a squared sine squared theta, you can factor out an a. All right, so in this scenario, let's assume that a is a positive number, okay? So a can come out, and then you're left with 1 minus sine squared. Well, that's going to be the cosine squared, right? So this will be the square root of cosine squared. But notice that when we made this choice right here to use the right-hand side of the unit circle, then one of the consequences is that our cosine is always positive, right? Cosine's always positive over here. And since cosine's always positive, we don't have to worry about this absolute value. And we end up with this substitution right here, that our integrand can just be replaced with a cosine, a times cosine of theta. All right, so this is one of the substitutions that we will use frequently. There's 2 other versions of this, like I said. One of them is to turn everything around. So swap this and write this as x squared minus a squared. And at this point, we think, okay, well, this is slightly different, right? We switch this around. What do we want to do? Well, now we need a function whose, we need to make sure that the x, that the domain of this, is always greater than or equal to a, right? The absolute value. So it's between a and infinity and negative infinity and a, and negative a, right? And so that's going to be our goal there. So the substitution that we'll make is we'll call this secant theta, a times secant theta. And again, we can just write down the reason over here, because once we know this, then we can say, all right, well, a squared secant squared theta minus a squared, that whole thing just gets replaced with what? The a comes out again. It's kind of a common theme here. And then secant squared minus 1 is tangent squared. So we're going to want to make sure that whatever we choose, that we get tangent theta back. And so we've chosen our secant theta, right? So we need to think about, how do you get secant theta? Well, secant theta is 1 over cosine. So if we were to choose the right-hand side like we have up here, we actually wouldn't get all the possible values of x. We would only get positive x values back, right? So instead, for this one, what we'll do is we'll choose our domain, our theta, to be the first quadrant. That'll give us our positive x values. And then again, we'll choose the fourth quadrant. So the fourth quadrant. So this one's going to have to be broken up, right? So in this case, we have two different kind of domains for theta. So theta is between, by the way, it can't equal these endpoints, right? Those two, it's undefined. So theta is between 0 and pi over 2. And, or you could say or here, it starts back up at pi. It's allowed to equal pi. And then it goes over here, right? So that's when secant is -1, by the way. And then secant remains negative over here and goes to negative infinity as we approach. This would be 3 pi over 2 if we continue this interval like this. So those are the values of theta that we use to make sure that we get all the possible x values back. When we do that, notice that in quadrants 1 and 4, tangent's always positive, right? And so we get the same result that we got up here, which is when we take the square root, we don't have to worry about an absolute value on tangent, because in the two quadrants that we've restricted ourselves to, tangent is always going to be positive. All right, the other thing that we need to worry about if we compare with up here is we need to know what's the dx going to become, right? So dx is going to be the derivative of secant. This a is still here. Derivative of secant is secant theta tangent theta d theta. All right, so there's two of the three possibilities. Now, by the way, if you use this table, then what are you going to do? You're going to look at your integrand, and that's going to tell you to pick out one of these versions, right? Then you're going to say, okay, once I know my integrand, I'm going to pick, I'm going to set my x equal to a sine theta, and whatever that integrand is, that portion that made you choose, that becomes a cosine theta. And then, of course, you can't forget, you need this, right? And when does the domain come in? Well, partially, this is just for the setup to make sure that the choice is acceptable in the first place, but it is possible that you're going to need to draw some triangles and find some other trig functions when you're done computing, right, the integral. You're going to get maybe you'll get a tangent back or something. You'll have to figure out what is tangent in relation to all these things, and in terms of x, you got to get the x's back into your integral. And so in that case, it'll be important to remember where the domain is, the theta is. So finally, one last version here, and then we'll call it quits for this video. The last possibility is that this could equal, your integrand could be a squared plus x squared under the square root. And so for this one, this is similar to the example that we did in the last video. For this one, we're going to make the substitution. The x should be equal to tangent of theta. And we're going to use the right-hand side again, but remember, we can't use pi over 2 or negative pi over 2. So our theta will be strictly between negative pi over 2 and pi over 2. Our dx is going to have to be in the differential, right? So this will be secant squared theta d theta. And so these are the substitutions that we make. And then the reason is also a substitution, right? So the reason is that now, for this one, a squared plus a squared tangent squared theta, this is going to be equal to a, comes out, right? And again, on the right-hand side, so we're back on the red here, right? But on the right-hand side of the unit circle, secant is always positive. So when we take the square root of 1 plus tangent squared, that becomes the square root of secant squared, which is just secant theta in this case. All right, and so these are the substitutions that we are going to make. As you look through this table, a squared minus x squared, that's going to be sine. Okay, so a squared, you're going to make your x equal to a sine of theta. X squared minus a squared is secant theta. If you just remember the Pythagorean identity, you can remember all of these. The one that I remember by kind of a trick is this the last one here, because this is the only one with a plus sign, and a plus sign kind of looks like a t, right? So in this case, whenever you see the plus sign, you think plus tangent, okay, so you make your substitution be x equals tangent theta. That should be, I made a mistake here, right? We have an a here, we have an a here, so this should have been a tangent theta, and then a secant squared theta. That's the constant a from the integrand, right? Okay, and so I'm going to leave this here, but this is our table, and in the next video I'm going to do a bunch of examples using this table and the method of trig substitution to compute some integrals.